Introduction. Mohan and his father are standing in the balcony. They are talking the fresh air in early morning. Mohan watching something towards roadside curiously. Father, what is that grey color box type mounted on the electric pole? Son, that's a transformer. Okay, father, why it is used? Please tell me. Son, it is used to lower down the voltage or electricity. Electricity produced at power station is of many thousands volt. This transformer lower down the voltage to 220 volt for household and 440 volt for industrial purpose. Okay, father, and I wanna know more about this. To know more about this transformers, you have to explore the alternating current. Students, today we will study about the alternating current. Objectives. At the end of this lesson, you will be able to analyze series LCR circuit, represent impedance triangle, explain resonance in LCR circuit, describe sharpness of resonance in LCR circuit, calculate the power factor, describe LC oscillations, define transformers, understand types of transformers, explain energy losses in transformers. Series LCR circuit. Consider a circuit containing a resistor of resistance R, an inductor of inductance L, and a capacitor of capacitance C connected in series across an AC source. Let the source voltage is equal to Vm sin omega t. We apply Kirchhoff's rule in the loop to get V is equal to VR plus VL plus VC. The projection of VR at any instant on the vertical axis equals VR with its maximum value given by product of Im and R. The phasor VL leading the current phasor I by pi by 2 represents the voltage across the inductor. Its projection on the vertical axis at any instant equals VL with its maximum value given by product of Im and XL. The phasor VC lagging the current phasor I by pi by 2 represents the voltage across the capacitor. Its projection on the vertical axis at any instant equals Vc with its maximum value given by product of Im and Xc. Now we add the voltage phasors VR, VL and Vc vectorially to get the phasor V representing the net voltage across the circuit. V maximum is equal to under root of VR maximum square plus Vc maximum minus VL maximum square. The right triangle gives the equation for the maximum value of the net voltage and the phase angle. Tan phi is equal to Vc maximum minus VL maximum upon VR maximum. By using Ohm's law, we get Vm is equal to Im multiplied by under root of R square plus Xc minus XL square. We get the impedance of the circuit given by under root of R square plus XC minus XL square. Now the above equation becomes Vm is equal to product of Im and Z. We can also write this equation as Im is equal to Vm upon Z, or IRMS is equal to VRMS upon Z. Phasor diagram solution of series LCR circuit. The instantaneous current has the same value at all points of the circuit. I is equal to Im sin omega t plus phi, where phi is the phase difference between the voltage across the source and the current in the circuit. The instantaneous voltage across the three elements have the following phase reactions to the instantaneous current. The instantaneous voltage across the resistor VR is in phase with the instantaneous current I. The instantaneous voltage across the inductor VL leads the current I by pi by 2. The instantaneous voltage across the capacitor Vc lags the current I by pi by 2. Impedance triangle. Impedance triangle can be used to calculate impedance when resistance, inductance and capacitance all are present in the circuit, and the total reactance is the difference between the inductive reactants and capacitive reactants. Z is equal to under root of R square plus Xc minus XL square. A right triangle with the impedance Z as it hypotenuses the quantity XL minus Xc is called the reactance of the circuit, denoted by X. Tan phi is equal to Xc minus XL upon R. Resonance in LCR circuit. Resonance occurs in systems which have a tendency to oscillate at a particular frequency when a periodic external force whose frequency exactly equals this natural frequency is applied to the system. At resonance, the energy delivered by the external periodic force to the system is at the maximum rate possible, resulting in a large amplitude oscillatory motion of the system. The frequency omega naught at which the current amplitude becomes maximum is called the resonant frequency of the circuit. Omega naught is equal to 1 upon under root LC. At resonance, the amplitude of the current oscillations is determined entirely by the resistance R. Im max is equal to Vm upon R. At resonance, the instantaneous current I and the voltage V in LCR circuit are in phase. Dear students who does not like, subscribe and share the channel, please do now. Thank you. Sharpness of resonance in LCR circuit. The effect of resistance on electrical resonance is to make the sharpness of the resonance curve less pronounced. The smaller the resistance, the sharper is the resonance curve. The quality factor Q of the circuit is given by omega naught 1 upon R or 1 upon omega naught CR. Quality factor is used to describe the sharpness of resonance peaks. If R is small or 1 is large, the quality factor Q is large, signifying that the resonance is sharper and the circuit is more selective. Example. Let's take an example of resonance in LCR circuit. Obtain the resonant frequency and Q factor of a series of LCR circuit with L is equal to 3 Henry, C is equal to 27 microfarad and R is equal to 7.4 ohm. It is desired to improve the sharpness of the circuit by reducing its full width at maximum value by a factor 2. Let's see the solution. Given values are L is equal to 3 Henry, C is equal to 27 into 10 raised to the power minus 6 farad, R is equal to 7.4 ohm. We know that resonance frequency is given by 1 upon under root LC. Now putting the values, we get resonance frequency equals to 111 radian per second. Q factor is equal to omega R1 upon R. Now putting the values and we get Q factor equals to 45. As Q is inversely proportional to R, so R should be half in order to double Q. The power factor. We know that an AC voltage V is equal to Vm sin omega t applied across an LCR series circuit drives a current in the circuit given by Im sin omega t plus phi. The instantaneous power dissipated in the circuit is P is equal to Vi. The time average of the power over a complete cycle is given by V RMS into I RMS into cos phi. We can conclude that the average power delivered to the circuit depends not only on the voltage and current but also on the cosine of the phase angle phi between them. The term cos phi is called the power factor of the circuit. From the impedance diagram, we can define the power factor as cos phi is equal to R upon Z, which is equal to R upon under root R square plus XL minus XC square. Now we are using both above equations to calculate time average of the power over the complete cycle. P bar is equal to product of IRMS square and R. Dear students, please like, subscribe and share the channel, and also share this channel with your friends and family members. Thank you. Power factor in different circuits. Case 1. Resistive circuit. If the circuit contains only the resistor, then phi is equal to 0. value of cos phi is equal to 1. There is maximum power dissipation. P bar is equal to product of Vrms and Irms. Case 2. Purely inductive or capacitive circuit. If the circuit contains only the inductor or capacitor, then phi is equal to minus pi by 2 or pi by 2. Value of cos phi is equal to 0. There is no power dissipation. P bar is equal to 0. Case 3. LCR series circuit. If the circuit contains the inductor, capacitor and resistor, then cos phi lies between 0 and 1. There is always power dissipation in the circuit. P bar is equal to product of Vrms, Irms and cos phi. Case 4. Power dissipated at resonance in circuit. Power is only dissipated in the resistor. No power is dissipated as heat by either an inductor or a capacitor in an LCR circuit. LC oscillations. We assume that initially the capacitor C of the LC circuit carries a charge Q and the current I in the inductor is 0. At that time, the energy stored in the electric field of the capacitor is UE and the energy stored in the inductor UB is 0. The capacitor now begins to discharge through the inductor and the current begins to flow anti-clockwise. The charge of the capacitor decreases but the energy in the magnetic field of the inductor increases. The energy is transferred from the capacitor to the inductor. The energy stored in the capacitor is transferred entirely to the magnetic field of the inductor. At this stage, there is maximum value of current in the inductor. Now, energy flows from the inductor back to the capacitor as the electric field builds up again. Complete transfer of energy takes place from inductor to the capacitor. This situation is just like the initial situation except that the capacitor is charged oppositely. The capacitor will begin to discharge. Again, the current will now flow in clockwise direction. The energy stored in the capacitor is transferred entirely to the magnetic field of the inductor. Energy now flows from the inductor back to the capacitor. The energy is continuously shuttled back and forth between the electric field in the capacitor and the magnetic field in the inductor. The process continues at a definite frequency B. If no resistance is present in LC circuit, then the LC oscillations will continue indefinitely. Transformers. A transformer is a device used to lower or raise the amplitude of AC voltage and current. A transformer consists of a soft iron core on which two coils of wire are wound. One is called the primary with NP turns and the other is called the secondary with NS turns. The primary is connected to the AC EMF source. The secondary provides the output of the transformer. The soft iron core is used to increase the magnetic flux and to provide a medium in which nearly all the flux through one coil passes through the other. Working of transformer. When an input AC voltage is applied to the primary, the alternating current in it establishes a changing magnetic field in the iron core. Since the magnetic field is changing, the flux through the primary and secondary is also changing, and hence an EMF is induced in both coils. Let phi is the magnetic flux through each turn of both the coils. The induced EMF in the secondary is due to mutual induction. ES is equal to minus NS d phi by dt. The induced EMF in the primary coil arises from self-induction. EP is equal to minus NP d phi by dt. Now dividing both the equations and get ES by EP is equal to NS by NP. This equation is known as the transformer equation. It can be written in the form of terminal voltage as Vs by Vp is equal to Ns by Np. The ratio Ns by Np is called the turns ratio of the transformer. Types of transformers are of following two types: a step-up transformer. When the secondary voltage is greater than the primary voltage, the transformer is referred to as a step-up transformer. A step-down transformer. When the secondary voltage is less than the primary voltage, the transformer is referred to as a step-down transformer. A transformer that steps up the voltage simultaneously steps down the current, and a transformer that steps down the voltage steps up the current. Is by Ip is equal to Vp by Vs is equal to Np by Ns. Applications of transformer. It is used to increase voltage before transmitting electrical energy over long distance through wires. They have saved the electricity supply industry, permitting generation to be located remotely from points of demand. They are also used extensively in electronic products to step down the supply voltage to a level suitable for the low voltage circuits they contain. Signal and audio transformers are used to couple stages of amplifiers and to match devices such as microphones and record players to the input of amplifiers. Audio transformers allow telephone circuits to carry on a two-way conversation over a single pair of wires. Energy losses in transformer. There are some energy losses in transformer as following: flux leakage. Energy is lost when not all the flux produced by the primary pass through the secondary. This loss can be reduced by winding the primary and secondary coils one over the other. Resistance of the windings. Energy is lost due to the heat produced in the windings. This loss can be reduced by using thick wires. Eddy currents. Energy in the form of heat is lost due to the eddy currents in the iron core. This loss is reduced by using laminated core. Hysteresis. Energy is also lost in the form of heat during the cycles of magnetization and demagnetization of the iron core. This loss can be minimized by using core material having narrow hysteresis loop. The use of soft iron core limits hysteresis loss and flux leakage. Did you know? Parallel resonant circuit can be used as a rejector or filter circuit. Such circuits are used in radio transmitters. A capacitor could produce electrical oscillations was discovered in 1826 by French scientist Félix Savary. Radio frequency transformers are designed to operate efficiently within a narrow range of high frequencies. Summary. Let us summarize what we have learned so far. In series LCR circuit, the instantaneous voltage across the resistor is in phase with the instantaneous current. The instantaneous voltage across the inductor leads the current by pi by 2. The instantaneous voltage across the capacitor lags the current by pi by 2. Impedance triangle is used to calculate impedance when resistance, inductance and capacitance all are present in the circuit. At resonance, the energy delivered by the external periodic force to the system is at the maximum rate possible, resulting in a large amplitude oscillatory motion of the system. At resonance, the instantaneous current I and the voltage V in the LCR circuit are in phase. A transformer is a device used to lower or raise the amplitude of AC voltage and current. In transformer, energy is lost due to heat produced in the windings. This loss can be reduced by using thick wires. The use of soft iron core limits hysteresis loss and flux leakage.